Okay, so here we start. I'm interested in small signal model for BJT, and to do this, I apply VBE. VBE is equal to VBE plus DC. So net VBE is equal to DC VBE plus AC VBE, which is small VBE. So what I'm interested in this value. So what I'll do is I know the DC value as such. So I'll write total VBE wherever I want, subtract with capital DC values from that. So whatever will remainder will be for the small signal. Okay, so that's the technique which we applied PN junctions, we'll repeat here. But before doing this, I'm more interested to know, can I write my IBT is something like this? This is an relevant because we are looking for a time dependent solution, and I am interested to know, can I write this equation which I wrote, or rather any I, you need not write even base. As long as your perturbation is small v, it's okay, but if that becomes larger, then the large signal noise is larger than the small signal. Okay, so I want to see that can I use this relation. Since I know Q's, I can derive Q by the profile of poles or electrons in base. So if I know Q, and if I can write instantaneous current I, change in Q by tau, change in Q with time plus Q by tau, then I'll be able to solve this equation much faster because time dependence I can see quickly. So to do this, I do simple this. If all of you are aware, 1 upon Q dj by dx, let's say for P, any device, minus delta P by, even right now I may not put anything. Only thing is now I start writing both as a function of time and space, delta Ext by Pt. What is this equation called? Continuity equation. Okay, this is the continuity equation. So I can write djp by dt dx is equal to delta p xt by tau plus q times tau p, in case this q I brought on this side, plus q dt by dt xt. So if I need to find Jp xt first, so that's the current Jp xt. So I should do this as integral from anywhere to x, djp by dxt x into dx, simple integral of dj by dx, and then on this side integral q delta p xt by tau p dx plus q times d by dt integral 0 to x p xt dx. if I write in terms of currents, what should I do? If I have current density and I want current, multiply area everywhere and I get I's. So even if I remove P for the heck of it, right now it can be true for N transport or a P transport. So in generalize I can say IXT or IT, essentially what I am writing is, this is of course how much? JPX or IPX. DX cancel, JP, so only JPX, okay. Or you may say if it is I, then it is IPX minus IP0, P of course is built in. Area I will now multiply QA integral 0 to x, I will keep at that itself, delta P xt y tau P dx plus QA 0 to x. This of course I can expand, but I don't want right now. So this is a statement of continuity. Yes, that was the I said I want current to be replaced by this kind of relationship, or rather in terms of charges, and to get this I started with the continuity. Is that okay? So I want to prove that that relationship is what really I am looking for. Is that okay, Raj? It is always true, I have never said it's not true. The proof is this, because you know from where it has come, I want to always show that the continuity equation is the one which is relating to that. Because in continuity equation, the only one which says time dependence of its charge flow is related to its charge by recombination plus rate change. That continuity word which I showed in a box is what I am proving again using this. Is that clear? So that's the way. We have already derived to some extent, it's visible directly, but I just want to tell you from where these equations are normally written. So now this is not given in a book, they write this and they write some sentences. So I say even numerically, I can get this relationship right here. Is that clear to you? So that's my way of looking. And then I can give you at x is equal to 0 and x is equal to infinity two boundary conditions. So IP0t is IT and IP x is equal to infinity t, I will say 0, because if the bound is there, the current at the other end is 0. Okay, there is no diffusion ahead. Okay. So I said this is there for IT. This term of course will be remembered. And what is this term? QA, excess charge, divided by tau. This is QA into charge is Q by tau. This integral of this delta px into Q is the Qn divided by tau. By same argument, QA into this, integrate over this to this, differential of that is dq by dt. So this term is essentially Qn by tau p, and this term is dqn by dt is IT. So a continuity equation states that the rate change of in a given box is proportional to the gradient of the current or gradient of the flux going through plus minus the recombination going through. This is the statement which we made in continuity equation relates to this. Is that clear? So these relationships which you see in books, if someone asks you from where I got it, this is the way you can always get. So there is no statement just making statement. I can always show you that this is the value which I can derive. This, as I say, I normally do it for people who, if they accept it, fine. If they don't, please accept here. Okay, so what Rastogi was saying is obvious, yeah, I knew it's obvious, but to some it may not be obvious, so I thought make it obvious. Okay, so let's do this. What is my interest is, I also said last time delta PE, which is the excess this, can be written as, this is for PN junction, I am just repeating, please remember I am just repeating what I did earlier, 1 plus QVBE by KT. What is delta PE? Pn0 minus Pno, Pn0 is Pn0 e to the power QVB by KT minus 1. VB there you substitute this. Okay, with this will give you a DC part plus AC part. So that's the way that relationship was. Is that clear to you? I repeat if you are not still got it. Pn0 minus Pno is the excess, so Pno e to the power QVB by KT minus 1, and this VB I expanded then e to the power QVB plus VB by KT minus 1. Then I say this is expansion QVB, this minus 1 can give you DC, and this exponential QVB by KT is 1 plus QVB by KT, under what condition? That VB is much smaller compared to KT by Q, and that's the number I am talking. What is VB maximum allowed? Less than KT by Q, which is 25 millivolts. So a small signal analysis is valid if my signal is much less than 25 millivolts. If it is not, you can still solve what is called large signal analysis by writing the actual equations and solve for it. Nothing goes wrong otherwise. But if you are using this model, the condition is VB must be, or small AC signal should be smaller than 25 millivolts typically. So what is the typical signals we use? Few millivolts to tens of millivolts or 20, 15s or 20s of millivolts, but never 50 or 100 millivolt signals are used with this kind of approximation. Definitely yes, but essentially the way we do it, noise is always taken care because it's a DC value plus small signal. If you are at 0, yes, the noise will superimpose. But you are 600 millivolts or 700 millivolts DC over which this is coming, so that will actually plus minus very small value. So it's a net noise will come, but that will be smaller compared to the amplifier. So I am not saying it is not, it is true. We do eliminate noise by some other technique, some other day in some other course. It's called noise elimination. Okay, so is that point clear? So I just thought I will repeat those who still doubt me that kaisa kiya. So we say the Q and T therefore is equal to half Q A W, W is the width of this, डेल्टा PET एक ट्रायंगल का एरिया है, इज दैट करेक्ट? ये ट्रायंगल का बेस डिस्ट्रीब्यूशन ट्रायंगल का एरिया है, इज दैट करेक्ट? डेल्टा PET into QA into W, this is the charge in the base, time depend, this is called instantaneous charge at any time t is that correct? Now if I know how this, I can replace this total one, you can say this half QAW delta PEDC plus QVB, whatever I have written, into 1 plus QVB by QC. This is the DC value multiplied by this. What is this value essentially? Anyone? कितना होता है ये? एकदम बोलते आना चाहिए. IV is this divided by tau, so IV tau is this. Is that correct? Okay, so this is my QNT, and if you want Qn by tau, then you just divide by this. So if I now write IBT, okay, or capital IBT, let's say, then Qn total divided by tau p plus delta Qn by dt उसको dqn by dt कर सकते हैं वो एक्सप्रेशन से, then that gets IB tau p 1 plus q by kt dVb by kt dV by dt. 1 का तो डिफरेंशियल नहीं होगा ना, सॉरी. ओके, नाउ if I do this, substitute that into the equation which I wrote. dq by dt is known, q is known, q by tau is known, q by dt is known, so I know the net current I, which I wrote directly for you, and just write down what I write. A small signal IBT is how much? Can you tell me what will be small signal IBT? Yes? Total base current minus DC current. Is that correct? Net current minus the DC current is the AC current. So using that, I solve this, and what I am going to get is the following. QIB by KT into VBE plus 2/3 QIB by KT into tau p into dVbe by kt, dt. अच्छा, अभी ये इक्वेशन देखो प्लीज. द बेस टाइम डिपेंडेंट बेस करंट is related to AC value of VBE plus a differential of AC voltage. Is that correct? So what should be the unit of this QIB by KT to make it current? This must be G. Conductance into voltage must be the current. So this has a unit of conductance. So I call this value as G pi. Conductance pi will say, because the model which we are going to write is called hybrid pi model. Why this pi word could come, can you think? Pi ऐसा है, सर्किट में दो ऐसे कंपोनेंट और एक बीच में ऐसा है, इसलिए पाई बोल दिया, हाइब्रिड पाई. ओके, तो ये जी पाई वीबीआर, इसका क्या यूनिट होगा? करंट के लिए dV by dt है, तो उसका प्री फैक्टर क्या होगा करंट लाने के लिए? dV by dt into what is current? C dV by dt is the current. Okay, so this is essentially C pi dV by kt. तो आपको अभी दो कंपोनेंट इनपुट के साइड में दिखे. विच आर द टू कंपोनेंट्स आई कुड सी ऑन द इनपुट साइड? इफ द बेस करंट इज इनपुटेड फॉर कॉमन एमीटर सर्किट, I see to get my this current IB for a given VBE, there must be a resistance shunted by a capacitance. Is that correct? If VB is there, so obviously there must be something like this. ऐसा कुछ होना चाहिए, ऐसा होना चाहिए ना. तो ये इनपुट सर्किट का तो ये आ गया मेरे पास, अभी ऐसा दिखना चाहिए मेरे. इज दैट क्लियर? तो वन पार्ट ऑफ द emitter common emitter circuit, common emitter configuration on the base side is it should have a resistance shunted by, or across it there is a capacitance, which is these values are AC value. Please take it, C pi, G pi R or C pi R pi R, AC values, but they depend on what? DC values. Is that correct? They depend on the DC value. So this is what I kept on saying, small signal parameters are functions of the DC values at which device is biased. Where it is biased will give me the value of their equivalent AC parameter. Is that correct? That word in circuit we keep on saying bias the device here, that bias means how much is the IC or VC or IB I am fixing DC, that may give me the value of small signal equivalent parts. Is that correct? Same way we did in the case of MOSFET, even there we said IDS decides GM, IDS decides R0. Is that correct? So capital I, whatever we say, actually decides the small signal value. And that's why we said it, because if you see IV characteristics and if it is not linear, at what point you take a slope will decide the different value, because slope is not same. So there is a curve. What I am telling you, this theory is independent of anything. You look any function versus x. With this, so at every value df by dx is different. So at what point I am not only differential is essentially what we say AC values. Okay. So AC terms are essentially decided by where is your DC point. Is that correct? This is called quiescent point, or where you actually bias your device. Is that correct? So in circuits, next semester when you do courses, this you must realize that the first thing we have to do in a circuit is to decide where is the biasing point. Okay. That is where it gets you the AC part. Is that correct? Signal may be anything, small is or whatever frequency. So once we got IB, okay, ये रहने दो, आपके पास तो ये फंक्शन लिखे हुए हैं, तो मेरे पास नहीं है, फिर भी आप लिख सकते हैं. Okay. Similarly, I can say IC, total collector current, AC collector current can be written as QIB by beta divided by AT into VT. Beta times IB is IC, nothing very great. But what is this value? Capital IC. अब इसके यूनिट क्या हो सकते हैं? IC is the collector current which is controlled by the base current or base voltage. VB is the base emitter voltage. Which side is this? Input side. This is the current at the output side. So the parameter which I am now looking at the output side, collector current is my, what is this parameter will be? GM. Okay. So now few things which we are looking for, that what is the input side, what is the output side. So if we know this, then writing the equivalent circuit is not very difficult. Right now I am looking for, we can change this I am looking for this kind of circuit. Okay. So I figured out I have a base which is external terminal. Okay. But actually there is a resistance called base spreading resistance. This comes from the technology because there is a relative length up to which first carriers have to travel. So the resistance of the base region is called base spreading resistance, which is always present, maybe less 10 ohms to 100 ohms, depends on the different technology I use. So actual base is here, or rather maybe B dash is here. Is that correct? So in many cases RBB dash can be taken here if I apply a AC signal here like this. So I say RS plus RBB dash is the net series resistance and start at B dash. If you start, you don't have to always do this, but if this is not known earlier, so I say okay, this is RBB dash. From here, or maybe we change otherwise so that no confusion are there. From here, what are the two components I am looking for? R phi that okay? R pi C. Now these are not the only capacitances here. Okay. Now there is another capacitance I see which I call CD. What is this capacitance? Your time dependent space charge, time dependent charge in the base, time dependent. Change in any charge is what it gives. Change in charge with voltage, what is it called? Capacitance. This is called diffusion capacitance. Base emitter junction is forward bias. You are pushing the carrier. Change in base charge with time gives you another capacitance which we derived earlier called the diffusion capacitance, CS or CD, whichever symbol you use. There is another capacitance I see. What could be this? चलो आप जरा जल्दी जल्दी सोचो यार, बहुत टाइम मत लो क्योंकि इसको खत्म तो करना है आज मुझे. T प्लस N T फॉरवर्ड बायस है, रिवर्स बायस है. ये क्या है? डिप्लीशन लेयर है, इसका अपना कैपेसिटेंस है CJ. तो देयर इज ए CJE which is also voltage dependent capacitance, depends on VBE or V pi. Okay. So there is a CJE is the another capacitance I see. If you see really the values among all of them, this will dominate. This is the highest value. Okay. But as far as model is concerned, we may like to put all three of them here. At best what we will say, okay, all three in parallel is equal to Cin. Or maybe you call it C pi dash here and final is C pi, which is C pi dash plus CD plus CJE. Is that clear? So we may consolidate into a one capacitance because they are all in parallel. Is that correct? So it's okay. But essentially there are three different components sitting there. This is the first, which is still we are at what point? Base. The lower part is emitter. There is also emitter resistor, but right now छोड़ दें. नहीं तो एक और ऐसा करते एक और ग्राउंड मान अभी छोड़ दें. Okay. Now this is my input. Oh sorry. ठीक है. अब if you see my device once again, यहाँ बना लेते हैं. This is my junction, this is my junction. Okay. There is a capacitance at the collector end, base collector junction is a capacitance. Is that correct? Now there is another charge, capacitance related or time related, you will see later. But how much is this? Can you tell me what is this capacitance will be? And this capacitance is called C mu. How much it is? Epsilon for silicon, that is Ks epsilon naught. This into area by what? XDC, whatever XDC is the because of the depletion layer, because of the collector VBC is whatever is the thickness, that divided by this is the capacitance at the collector base. Which area it is? Base collector. This was your base. If you are very fussy, you shouldn't be actually. You may also say कि सर सिर्फ कैपेसिटेंस में नहीं, ये तो रिवर्स बायस डायोड है, इसका अपना एक रेजिस्टेंस है. तो यदि आप बहुत ज़्यादा ये हो तो ये भी लगा सकते. कितना होगा आदमी? Tens of megohm to hundreds of megohm. Reverse bias diode, very small currents. Is that correct? So if you are really very fussy, small signal, you say okay, आर्मी भी है. But generally हम लेते नहीं है because it's much higher than the impedance given by C mu. जिसका छोटा होगा वही इसमें निकलने वाला है ना, इसलिए पाथ वही है. पर एक बता दिया कि ऐसा भी हो सकता है. अब ये आ गया आपका कलेक्टर और मे बी कॉल इट कलेक्टर, और आगे जाके एक थोड़ा सा RCC डैश को RC बोलते थे, वो एक्चुअल कलेक्टर एक्सटर्नल है। अच्छा यहाँ क्या क्या दिखेगा, अभी वो रिलेशनशिप बताया ना मैंने, GMBB करंट सोर्स कलेक्टर टू एमिटर, करंट सोर्स। GMBB को थोड़ा सा और ट्रिक कर सकते। कैन यू टेल मी इफ दिस रिलेशन इज वैलिड? है कि नहीं है? अभी लिखा है ना सब जगह यार, अभी क्या तुम जल्दी जल्दी सोचा करो भाई। तो GM R पाई जो है वो बीटा होता है। तो यदि आपको किसी सर्किट में बीटा बता दिया गया और यदि यू नो व्हाट बेस करंट यू आर माइसिंग, so what essentially I am giving you R pi values indirectly I gave you. I may never say I have given you an R pi value. I know my bias, so I know my IB, I know my R pi immediately. Is that correct? The relation which I hold is this, beta is. अब यदि उसको यदि GMBBA को रिप्लेस करना है बीटा में तो क्या करेंगे? चलो आप सोच के बताओ, मैं तो लिख देता हूं यहां पर। If IB is the current entering here and capacitance are neglected as far as VB is concerned, IB R pi is VB. Replace VB by IB R pi, GM replace karo beta by R pi. I repeat what I am saying. GM R pi is beta by R pi, VB R pi, and this is I, इसको IB लिखना है into R pi जो VB, so beta IB. So sometimes you write current source as beta times IB, sometimes you can write as GMBB, whichever way you wish to write, both are correct. Okay, both are correct. So why I am saying, because in circuit people keep exchanging things as and when they want, because ये दिया हुआ है directly उसका वहाँ करंट पता है, we came here, वहाँ voltage पता है, we use this. Whichever the way you solve the circuit, why these two different techniques I am suggesting? किरचॉफ का कौन सा लॉ यूज करना चाहेंगे, मेश इक्वेशन या नोडल इक्वेशन, जो भी यूज करने हैं उसके लिए दोनों मिल सकते हैं आपको. Is that clear? That's how you actually use the actual equivalence. Okay, so this is your beta IB. There is a capacitance. What is this capacitance should be? Collector to emitter. Actually this capacitance is little funny. This is not real capacitance, but you can see from here what I am saying. अब ये देखो थोड़ा सा थ्योरी है. एमीटर जंक्शन से यहाँ जाने तक there is some finite time required. Is that correct? The time will be decided by this capacitance, transit through this capacitance, change in charge here, further transiting on this. Whenever there is a RC time constant from emitter to collector, R is the resistance and time is required to move through carriers, charge carriers. It is equivalently saying there is a capacitance. I repeat, RC is time constant. If I have a time and I have R, time dependent, time is talking, so I am essentially saying I am looking equivalent of a capacitance. Is that clear? So sometimes, no, this is external, between collector and emitter. That is what I am saying. So many a times we never use it, but if you see some advanced books or some per se, even never, but let's say, then कहीं सर आपने कभी नहीं बताया कि उधर भी एक कैपेसिटर है, इसलिए बता दिया कि ऐसा भी है. थ्योरी में थ्योरी है, आप इसको भूल जाओ, बट मैंने आपको बता दिया कि बहुत कुछ है, बहुत कुछ हो. Okay, So this is called small signal equivalent model of this. Is that clear to you? Now, अब थोड़ा सा क्या करें, एक समझो एक एम्पलीफायर लें, now one word we use, low frequency small signal hybrid pi. Why it is called hybrid pi? One arm, second arm, third arm, so looks like pi, therefore it's called pi. Hybrid word is used for what? कब hybrid बोलते हो आप? एक नेटवर्क है, एक इनपुट है, एक आउटपुट है, यदि वो सेम है, वोल्टेज करंट, तो दे आर नॉट हाइब्रिड. बट एक करंट है, दूसरा वोल्टेज है, ये वोल्टेज है, वो करंट है, तो ये हाइब्रिड हो गया. ये क्योंकि एक साइड से हम करंट ले रहे हैं, वोल्टेज ले रहे हैं, और दूसरे जगह करंट दिखा देते हैं, इसलिए इसको बोलते हैं हाइब्रिड इक्विवेलेंट. क्या होगा इसका हाइब्रिड पाई मॉडल? कैन यू टेल मी नाउ क्विकली, एंड assume right now RBB dash is also 0 for the sake of it, or if you wish you can keep it, maybe we can keep it. Low frequency means 1 upon omega c is large enough to show open circuit everywhere. Okay, assume this. Low frequency 1 upon omega c, the impedance is very large. So R के across open, ऊपर भी open, so all capacitance get out of it. So in most cases, when I quickly, what is this value? Therefore, this lower frequency values are many times called DC gain, or which we are now calling DC. Why it's called DC? Means the frequency dependent terms were neglected by me, so it is called DC. But remember, this is not DC, this is small signal AC equivalent. So these words in analog people keep saying DC. There is no DC there. Okay? Amplification is only of AC signal. But since the terms which are frequency dependent, I left them out. So it was many times called as DC values. Okay. Okay, so here is the first amplifier I want to check. ये मॉडल समझ में आ गया? ये IB करंट है, IB इंटू आर पाई, तो हाँ नहीं ऐसा है कि you are right, part of the voltage, but these impedances are normally compared to R pi maximum current. You are right, will flow through this. So the drop across flowing here, what he is saying is true. This is IB1, this is IB2, this is IB3. Yes, you are right, very correct. But the impedance space there, 1 upon j omega c, their contribution to this is smaller, and therefore we say most of the current will flow through R pi, but your statement is correct. You are very correct. तो एक एम्पलीफायर है, अभी तक हम बार बार पीएनपी डिवाइस कर रहे हैं, और जब भी मैं सर्किट दिखाता हूँ वो एक एनपीएन ही लेता हूँ. अच्छा, क्यों एनपीएन अच्छा होगा पीएनपी से? Other day I said you don't never say the word which is always said. Okay, it is true, but it is the diffusion coefficient of electrons which matter, which is higher than the diffusion coefficient for holes. Okay. That's not the only reason. The gamma of an NPN is higher than gamma of a PNP. That is, emitter efficiency of the everything else, NPN transistors show larger gammas. Not very high, but higher. The process steps in NPN are lesser compared to PNP, one step less, one mass less. $10,000 कम, $10,000 भी नहीं, $1 million का एक मास है. So it's a huge money. So NPN transistors are always preferred, and since their timings are faster, their speeds are also for the same size everything they will be faster than PNP. वो होल्स ऐसे ऐसे जा रहे हैं, इलेक्ट्रॉन ऐसे जा रहे हैं, तो फर्क पड़ता है. ओके, अभी हमने इसको कहा कि एक रेजिस्टेंस लगाया, एक Vin लगाया, सिग्नल दिया, ये RS है. Let us say this is the I. Now in this what I said, I actually must fix my capital VB. So there are different ways of fixing. One is actually ऐसा ऐसा कर सकते हैं, एक यहाँ भी resistance लगा सकते हैं, बहुत कुछ. There are different biasing systems which we will use, and for AC they neglect all of that part. Please remember, but in AC analysis the resistances cannot be removed. वो लगे हैं तो लगे ही हैं, अभी उसको कैसे निकालेंगे. तो सर्किट सॉल्व करते समय उन्हें भूलना नहीं था. अभी मैंने यहाँ मैं नहीं ले रहा हूँ, बट एक्चुअल सर्किट में कोई कंपोनेंट कैपेसिटेंस बहुत बार छोड़ सकते हैं, बिकॉज यदि RE को शंट किया, ये बहुत बड़ा कैपेसिटेंस है, तो 1/j⍵c विल बी, इसको बाईपास कर सकते हैं. तो यहाँ इन दोनों को मिलके ऐसा भी ऐसा करते हैं हम सर्किट. बट अभी आप सोचिए कि ऐसा कुछ नहीं है, बायस हो गया है, एक IB इज द बायस करंट. ये मेरा V0 है. तो यहां पर अभी क्या है, इक्विवेलेंट, सब कुछ छोड़ छाड़ के इधर एक इनपुट सिग्नल लगा दिया मैंने, Vin RS. Is that okay? So what is VB now? अब बोलो जरा, वो आदमी परेशान था ना, उसको बोलो अभी कितना है VB. VB यहाँ जो करंट फ्लो करेगा, वोल्टेज चाहिए आपको, तो क्या होगा, IB times R pi. Is that correct? But how is it related to Vin? So essentially you can say R pi upon R pi plus RBB dash plus RS times Vin is VB. Is that okay? Potential divider, this resistance divided by the net resistance multiplied by voltage is the voltage across the R pi. Simple voltage divider. तो ये आपका हो गया. यहाँ पर ये जो कैपेसिटेंस है, ये VB आपको पता लग गया. ओके, व्हाट इज V0 हियर? कितना होगा V0? ये VB V0, प्लीज जरा ध्यान से, करंट ऐसा फ्लो हो रहा है, तो माइनस GMVBE इंटू RC. पोलैरिटी ऊपर की प्लस माना है ना उसने, बट करंट तो ऐसा गया. So if that's so, I can write minus GMRC into Vin into R pi divided by R pi plus RBB dash plus RS, or to say V0 by Vin is called DC gain, is minus GM RC upon 1 plus RBB dash plus RS upon R pi. Is that okay? So the DC gain of a normal amplifier using a bipolar transistor is GM times the load divided. What is this value essentially telling you? This is essentially something like R pi upon, this is input ratio of the resistance seen by the input side, Rin. Okay. This is like saying output resistance by input resistance ratio है उन दोनों का. Okay. वो वैसा बिठाया गया. तो क्यों नाम बोला? What is transistor word coming from? Input to output resistance transfers, change. Therefore it was given a name transistor or transistor. ये इसका प्रूफ है. ओके, so any amplifier, अच्छा समझो, we say no, it's not frequency independent, that is not DC. Then what should you do? You must tell me these values, either by other data or directly. Then I will say, okay, I will have this, then P pi total you can say. पूरा नेटवर्क सॉल्व करो. इसमें कुछ और चीज हो रहा है. क्या चीज हो रहा है? करंट इधर भी जा रहा है और इधर भी जा रहा है. आउटपुट से भी करंट इधर आ रहा है और इधर जा रहा है. इसको क्या बोलते हैं? फीडबैक. सो दिस सर्किट हैज ए फीडबैक. ओके, okay, so this issue is very relevant, that this may change the actual gain at certain frequency, because this is frequency dependent gains now. V0 or gain will be functions of j omega or omega. Therefore, that is the actual gain, frequency dependent gain, which is used in most circuits. But that will contain this value by nature automatically, because this expression ऐसा बाहर निकल सकते हैं हमेशा. तो A0 टाइम्स समथिंग आपको फ्रीक्वेंसी डिपेंडेंट टर्म दिख सकता. ओके, तो फिर से बताता हूँ कि V0 बाय Vin इज एसेंशियली A ओमेगा. ओके, विल कम एज A0 प्लस फ्रीक्वेंसी टर्म F ओमेगा. इज दैट क्लियर? So A0 term will still appear. So at certain frequency that F omega will be 1, and as we increase F frequency higher, this will reduce. So net gain will also start reducing, up to which the gain does not change, remains A0, is called the bandwidth. The word used there is the bandwidth. A0 gain remains constant up to what frequency? That value we call as the bandwidth. If you increase frequency, gain will fall. So what is that together I am saying? Gain into bandwidth is constant, okay, for a given transistor. Ft actually is represent to some extent gain bandwidth product. Okay. As soon as you fix that for transistor, उससे ज़्यादा frequency नहीं use कर सकते. Why? Because then there will not be gain. Unity gain into bandwidth is the gain bandwidth. The maximum frequency which you can use is the gain bandwidth product frequency. Ft has. So remember, is that circuit का connection लगा? Ft which now we are going to derive is something coming from transistor side, okay, and that may limit my performance for the circuit. Therefore, when I make a choice of a transistor, I must make a choice whose Ft is higher, up to which therefore I want to work at. If I want to work at 100 megahertz, my Ft must be at least 1 gigahertz and above, or maybe higher, 10 gigahertz. इसको 80 to 100 times होना चाहिए, तब जाके बैंडविड्थ आपको सफिशिएंट मिले. इज दैट करेक्ट? तो ट्रांजिस्टर चॉइस, डिवाइस का चॉइस सर्किट के परफॉर्मेंस के लिए बहुत जरूरी. इज दैट क्लियर? दैट्स व्हाई आई एम रिलेटिंग. आई हैव ऑलवेज ट्राइड टू टेल यू, मे बी नेक्स्ट सेमेस्टर आई एम नॉट टीचिंग, लकी फॉर यू. एनालॉग पढ़ाता या डिजिटल तो मैं फिर आपको ये सब बताता. अभी मैं नहीं पढ़ा रहा हूँ तो मैं बोला अभी बताता. Okay, so please remember, sir, do not get into this that I am only keen about electrons, recombination. नहीं, actually I see this clearly in my mind. मुझे वो करना है, मैं यहाँ क्या करूँ? That is why all devices people use lot of theory to gain equivalent of that, because I can only solve this for the circuit. So I must get this, everything, and that's what the device is interested. Okay, last part of that. कोई बता सकता है कि डिफ्यूजन कैपेसिटेंस कैसे निकालते हैं? ये लास्ट पार्ट बिफोर, आई मीन लास्ट, इसमें से जो रह गया है वो क्या होगा? डिफ्यूजन कैपेसिटेंस क्या होता है? किससे चेंज हो रहा है डिफ्यूजन कैपेसिटेंस? इफ यू चेंज द बेस एमिटर वोल्टेज द चार्ज चेंजेस, द चेंज इन चार्ज विद चेंज इन VBE is called the diffusion capacitance. That's what we define. So typically we must say DQP, let's say for PN junction, DVBE is actually the diffusion capacitance. Q आपने निकाला था, अभी निकाला था, Q लिखा था ना लास्ट में Q, VB उसमें टर्म आ रही थी, PNO e to the power Q VB by kg टर्म आ रही थी. So this dq by dt which I have, dVB I directly write for you is essentially half QAW PNO Q by KT e to the power QVB by KT minus 1, and since one is very small compared to the other one, this is Q by KT QP by tau P into tau P. ये QP फिर से है सेकेंड टाइम, तो Q by KT IB into tau P. I repeat, what is this? This whole term again is QP. Okay. इसका डिफरेंशियल क्या है, इसलिए Q by KT आया, पर ये वन छोड़ के लिखा तो इक्वलेंटली सेइंग इट इज सेम एज QP. So QP by tau P into tau P. QP by tau P is IB, base current. This is into tau P. Can you tell this, what is the expression I am looking at? What is QIB by KT? V pi or 1 upon R pi into tau P. Can you see the units are correct? R into C is the time, R into C is the time, okay. So this diffusion capacitance is related to transistor parameters and biasing values, is that correct? R pi is a QIB by KT, तो बेस करंट कहाँ रखेंगे आप और लाइफ टाइम क्या है, that may decides your diffusion capacitance. तो वो निकालना पड़ता है हर बार जो बायस पर कितना CD. Is that correct? Please remember, this is your DC current which you will decide during from the input DC biasing. IB is fixed by you. Once you fix this, I know this. If I know this, and lifetime is always provided to you, then I know my diffusion capacity. How do you calculate these values? For given VBC and given VBE values, इसका डिप्लीशन लेयर कैलकुलेट करिए और एप्सिलॉन A by X लगा के जंक्शन कैपेसिटेंस. प्लीज रिमेंबर दिस फंक्शन ऑफ वोल्टेज at that voltage of DC, how much is the depletion layer, that you must calculate, and that's what CJE can evaluate. So all capacitances are decided by circuit as well as device parameters. क्योंकि इसको मैं कह रहा था तो एक इक्विवेलेंट आपको मैं इसका भी बता ही देता हूँ क्या होता है कि अभी C पाई टोटल लिख देता हूँ मैं R पाई. Now this has some relation, so that's why I want to do it. No, not C पाई, अभी C टोटल ही रखो. नो. अच्छा, ये जो मैं कर रहा हूँ ये क्या कर रहा हूं, आप मुझे थोड़ा बताएंगे क्या? पावर, आवाज आया तुम्हारा, क्या कर रहा हूं मैं? अभी थोड़ा पता लगा, सर्किट का अभी से ज्ञान दे रहा हूं मैं. इफ आई वांट टू सी द इनपुट साइड एनीथिंग, द फर्स्ट थिंग आई शॉर्ट द आउटपुट. इज दैट करेक्ट? सो आई डिड, मैं इस रेजिस्टर के यहाँ शॉर्ट मार दिया, ठीक है, यहाँ शॉर्ट मार दिया. As soon as I shorted this terminal, ये जो CMU था वो किधर चला गया? Between this terminal and the ground, because I have brought this to the ground ना. अब ये C में मेरा है ये जितने भी ये कैपेसिटेंस है C डैश पाई प्लस CD प्लस CJE प्लस CU, इज दैट करेक्ट? सभी कैपेसिटेंस अब पैरेलल हो गए, इज दैट करेक्ट? ओके, मैं थोड़ा ज्यादा ही सर्किट पढ़ा रहा हूँ आजकल, मैं कह रहा एनालॉग नेक्स्ट सेमेस्टर में आपको यह पार्ट ऐसे ही बता देना, हमने कर लिया है, उनसे फिर से मत सीखिए। ओके, अभी हाउ मच इज V पाई और VB, बताओ भाई जल्दी जल्दी। VB which is nothing but how much is that? Let us say IB is the current flowing here, small IB. ये तो पैरेलल कॉम्बिनेशन है, तो कितना इम्पीडेंस होगा? शंट कर रहे हैं, तो G पाई प्लस J ओमेगा C, G पाई प्लस J ओमेगा C इंटू IB is VB. So IB upon G पाई प्लस J ओमेगा C टोटल इज योर VB। दोस्तों की ठीक है? अब यदि मुझे ये VB पता लग गया तो ये करंट तो पता लगेगा ना, GM VB। ओके, but what is GM VB essentially is the output current. GM VB is the output current, nothing but IC. Is that correct? It's the collector current. तो अभी मैं थोड़ा सा और सिंपल मैथ्स करता हूँ। IC is GM VB, okay, but VB I have just calculated GM times IB divided by G pi plus J omega C। क्या होगा? अभी और क्या कर सकते हो? IC by IB, ये क्या वैल्यू है? कौन सा बीटा? AC बीटा। You need not say right now बीटा डैश रखो या बीटा AC लिखो, कुछ अर्जन नहीं। GM upon 1 upon R pi into J omega C, GM R pi 1 plus sorry, so 1 plus J omega R pi C. What is this value? Actually this is again beta DC. So DC is, please remember DC doesn't mean actual IC by IB. What is this DC? That I call beta 0. What is this beta DC means? Frequency independent term की वैल्यू। ये क्या है? RC क्या होता है? टाइम कांस्टेंट। ओमेगा is 2 pi into some frequency, 2 pi f. 1 upon time is frequency. तो इसको ऐसा भी लिख सकते हैं बीटा DC अपॉन 1 प्लस J ओमेगा बाय सम ओमेगा 0। अब समझो ओमेगा इज ओमेगा 0, व्हाट इज द मैग्नीट्यूड ऑफ बीटा AC? कितना होगा? 1 upon root 2 times beta D. मैग्नीट्यूड। तो अब इसको प्लॉट करके देखें क्या दिखता है मेरे को। ये सब चीजें इंटरेस्टिंग हैं और थोड़ा सीखो। तो इफ आई प्लॉट बीटा DC is this value and I am plotting beta versus frequency, क्या दिखेगा? If omega is less than omega 0, let's say this is my omega 0. If omega is much less than omega 0, what will be beta DC? Beta DC, because that magnitude wise the other term is small. So till this frequency, the gain is constant, beta DC, beta is beta DC, then it falls 3 dB down. What is this word 3 dB? 1 upon root 2 का log V2 by V1 किया तो 3 dB down. तो 3 dB down यहाँ से शुरू होता है और gain starts falling. As omega exceeds omega 0, the denominator will start increasing, so beta will start decreasing with frequency. Is that correct? तो एक सर्किट सर करते समय आपको यह पता होना चाहिए कि what is this omega 0 for you. Okay. Many times this is called omega beta. Instead of omega 0, books may call it omega beta. This is the value up to which beta is constant. Omega beta is the frequency up to which beta is constant. Beyond which beta falls. Is that correct? And what is this value? And beta DC is 1. It's it's actually omega t, which you can prove, look at it, beta times omega beta. And this frequency 1 upon 2 pi ft, ft is called figure of merit of any transistor, because beyond that if beta is less than 1, what's the point in having an amplifier or having a transistor? उससे थोड़ा तो ऊपर हो, isn't it? So that is the maximum frequency up to which transistor will act like a amplification device. Otherwise there is no point in using that as a device. Yes. DC. That is the max up to which gain. It's like telling gain bandwidth product का भी दूसरा नाम है. Gain into gain bandwidth product में unity gain हुआ तो bandwidth maximum. So what is the maximum frequency you can use for any circuit or device is this. This is called figure of merit. Is that correct? Now I will not prove it, but I will just tell you this omega t is, or ft, is essentially related to time, which is emitter to collector time. Some other day we may explain. Emitter to collector जाने में जितना टाइम लगता है सब कैपेसिटर सब ट्रांजिट करते हुए वो उसका 1 टाउ जो है वो ft होता है. तो जो डिवाइस के जितने पैरामीटर्स हैं, टाउ ईसी, चार्जिंग बेस एमिटर जंक्शन, ट्रांजिटिंग बेस जंक्शन, ट्रांजिट डिप्लीशन रीजन, ये सभी टाइम जो हैं ये सब मिलके एक्चुअली द मैक्सिमम फ्रीक्वेंसी आपको प्रोवाइड करते. इज दैट क्लियर? दैट्स वेरी इंपॉर्टेंट इन नोइंग. टू सम एक्सटेंट नोइंग दिस बीटा डीसी, बीटा जो दिया है इससे भी आप पता लगा सकते हैं कि कितना आपको एफटी में स्पेसिफाई होगा. तो यू रफली नो अप टू व्हाट फ्रीक्वेंसी this is usable as a beta value which you are doing. Is that this will be provided to you, this will be given to you, so indirectly I will provide you omega beta, and that's the frequency up to which beta should be used, because otherwise it will be frequency dependent terms. Please remember, in our equivalent circuit what beta is used, independent of frequency. Beta is independent of frequency. We don't want that to happen. We say okay, constant beta IB or GMVB, which is again beta related. So the maximum frequency you operate should be related to omega t by this, and typically, as I say, this will be around 100. So this is 100 times less than the given frequency to, okay, or more even, but at least 100. So यदि 1 GHz आपका FT दिया है तो आप 10 MHz तक ही ऑपरेट करिए. 10 GHz FT देते हैं तो 100 MHz कर लीजिए, और यदि 100 GHz देते हैं तो 1 GHz तक ऑपरेट करें. इज दैट करेक्ट? तो ट्रांजिस्टर कैसे चॉइस करते हैं, वो ऑपरेशनल फ्रीक्वेंसी और गिवन बीटा से यू नो इट वेयर अप टू यू कैन. इज दैट पावर क्लियर? टाउ ईसी, एमिटर टू कलेक्टर. आपको बताया था ना कि ट्रांजिस्टर में यहाँ से यहाँ तक जाने में जो टाइम लगता है कैरियर्स को, वो नेट ट्रांजिट टाइम बोलते हैं. बेस एमिटर जंक्शन चार्ज करना है, बेस ट्रांजिट करना है, कलेक्टर कैपेसिटेंस को चार्ज करना है, उसमें ट्रांजिट भी करना है, ये सब चारों टाइम जब जोड़ेंगे तो वो होता है टाउ ईसी. That is essentially the 1 upon ft is 1 upon tau effective. Is that correct? That decides the maximum frequency transistor can work to. Is that clear? This is something interesting because all of you must have by now. Okay, एक last word है, क्योंकि मैंने यहाँ ये एक्सप्रेशन लिख दिया है. ये GM/C जो है ना, अभी कहाँ लिखा है मैंने? ओके, इसको GM टर्म्स में मैं लिख सकता हूँ. बीटा DC और बीटा 0 इंटू ओमेगा बीटा is actually GM/C total or C pi T or call it whatever it is, और C कह लो, सिर्फ C लो. इस C में the maximum contribution come from CD. That's what I said. Diffusion capacitance is the largest contribution to the net C. तो प्रैक्टिकली हम ऐसा करते हैं, इसको CD लिखते हैं. GM C total has the largest contribution from diffusion capacitance. तब कैपेसिटेंस जोड़ रहा हूं, पर मैं ये कह रहा हूं कि these three compared to this are smaller, order smaller. So CD is the dominant one. So if I use this expression, then I don't know whether I have derived this or not, but I may now derive for you. CD can be written as GM W square by 2D, and therefore one can say this is 1 upon this is W square, sorry, 1 upon W square by 2D. क्या इसका ओमेगा, ये जो टर्म है ये फ्रीक्वेंसी डिपेंडेंट टर्म है ओमेगा टी, ये क्या यूनिट्स होंगे इसके? ओमेगा स्क्वायर बाय 2D, इधर फ्रीक्वेंसी लाना है मेरे को, टाइम होना चाहिए. So this time tau, and now I give that transit time is W square by D. So the transit time जो है बेस में ट्रांजिट करने का, that decides tau t. W square by 2D is the transit time. तो बहुत बार मैं ट्रांजिट टाइम नहीं दूंगा, आपको क्या बता सकता हूँ? W बेस विड्थ इतना है. यदि आपको बेस विड्थ दे दिया तो W square by 2D, D means DN or DP, जो भी PN NPN ट्रांसफर है. So I will be actually giving you tau t indirectly. Is that correct? If I also specify tau p, then what I am giving you? Beta. वो आपको है स्टेटमेंट में लिखा है जनरलाइज्ड बायसिंग कंडीशन बायस मॉडल, और इसका नाम है एबर स्मॉल मॉडल. प्लीज डू रीड दिस. This is part of the course. Eber's small model, generalized biasing. What is generalized biasing power? I said दोनों फॉरवर्ड बायस, ये रिवर्स, ये नॉर्मल, कुछ भी हो सकता है. उसका एक एक्सप्रेशन तैयार किया गया है, मॉडल बना है, दैट्स कॉल्ड Eber's small model. Please read that model. In case other day some may be explained, but otherwise you can. So this finishes the BJT. Okay. Next time we start with photonic devices. Okay. Next is 31st.